login accepted.
Hello, I think we can start. So once again, hello everybody. My name is Andrzej. I'm a solution architect at Software Mill, a fully remote Polish company. You might know us from our technical blog, Scala Times newsletter, Scalar conference, JVM blogger, which is maintained by our VP of engineering, and few of our open source projects. And the plan for today is to talk about event sourcing. I suppose that explaining the basics of this pattern is quite pointless. Everyone is more or less familiar with it. But there is no presentation about event sourcing without this slide, so let's get it over very quickly. In classic systems, the entity aggregate is persisted to the database as the most current state. In event sourcing, state in database not exist. I mean, you can save snapshot of the state, usually because of some performance reasons, but this is totally optional. What you are saving, what is your source of truth, are events. And when you reply events one by one, you will get exactly the same state as on the left side of the slide. But with events, you will also gain more business information. So item C was added and then removed from the order. It looks like a pretty interesting business information. Maybe we should send some voucher for this item to this user. Maybe we should send an email with a replacement for this item. Maybe this information is completely irrelevant for your business. What's crucial here is that you, as a developer, should not decide what information is important, what's not. You should store all business facts and provide necessary data when needed. And fun fact about event sourcing from Greg Young presentation. By the way, Greg Young is one of the event sourcing evangelists. If you don't know this gentleman, well, you should definitely Google him. So the fun fact is that humans have been using event sourcing for thousands of years. The first, let's say, implementation of event sourcing was found on clay tablets in Mesopotamia 9,000 years BC. And it was used for persisting marketplace transactions. So how many ships, grain, bread loaves were bought or sold. And this way, the Mesopotamian trader could very easily recalculate the state of possession, not by doing this manually. Another famous gentleman, Martin Fowler, in 2005 wrote a great article about event sourcing where you can read something like this. Enterprise applications that use event sourcing are rarer. I have seen a few applications or part of applications that use it. That's kind of sad. 11,000 years in total seems like enough time to validate some concept on production. And today we have 2021, and from my observations, which are obviously biased, but from my observations, this concept is finally getting more and more popular. Why? We are building completely different applications than 50, 20 years ago, and at some level, you simply don't have a choice. To scale, to be performant, you will end up with something very close to event sourcing or with full event sourcing adaptation. And why event sourcing? As I mentioned, with event sourcing, you will get complete log of all state changes in the system. This is especially useful for your business, no data is lost, but for you as a developer as well, debugging. Many times when I was trying to find a bug in my system, it was necessary to replay event by event and this way analyze what's going on with the application. And trust me, debugging this way is a completely different story. This is really, really nice experience. It's like time machine, but more real. But honestly, from my perspective, people invest in event sourcing because of these two reasons, so performance and scalability. This, of course, depends on the actual implementation. But let's say with event sourcing, you are slightly forced to use some techniques that will allow you to scale better in future and create more performant application. And the last point, finally, with event sourcing, the asynchronous, decoupled, event-driven communication works like a charm. OK, before we jump into more details, we need to talk about one more acronym, which is CQRS. Command query responsibility segregation. So in secure systems, the responsibility for handling commands and writes is separated from handling queries and reads. And this separation is not only on the software level, but also on the hardware level. So different deployments, different hosts, different databases, etc. And you can implement CQRS without event sourcing, but implementing event sourcing without CQRS is quite pointless. I mean, you can, why not? But it will be really hard to squeeze maximum potential from event sourcing without CQRS. That's why those two are implemented more or less together. Okay, during my journey with event sourcing application systems, I extracted few different levels of event sourcing adaptation. And the first level is so-called transactional event sourcing, where in one big transaction we are saving all our events and all read model updates, and yeah, that's it. Very easy to implement, zero magic, no eventual consistency, but the performance of such solution is limited. Of course, this huge transaction might be problematic at some point. Updating all read models might take some time. Also, you are forced to use the same database for events and for read models. Otherwise, you will end up with a distributed database, distributed transaction, which is even worse. Still, I'm not saying that you should never, ever implement event sourcing this way. Actually, this is a good starting point, especially if you are working on a startup or you are creating some proof of concept and you have no idea how many people will use your application. Maybe no one, like in one of my projects. That's why it's not worth to invest and create the most fancy architecture as the first iteration of the project. A few more links for you. Some links to articles of my friends about such implementation with all the details, code examples, etc., etc. So do not reinvent the wheel. Just follow the slide. Also, as a company, we created a very small open source project with such example of implementation. It's in Scala. If you are not so familiar with this language, you should be still able to grab the overall concepts and copy-paste them to your code base. So, quick summary. First level, easy to implement, easy to reason about, zero eventual consistency, but performance and scalability not so great. Second level. This time, the scope of this problematic transaction is much smaller. Now we are saving only events to our database in append-only fashion, and append-only writes is something that any database will love to handle. It will be extremely fast. Also, we introduced new piece, a projector, so something needs to read new events and update read models. So definitely, we improved the command handling side. We can also scale because we can launch hundreds of projectors. Unfortunately, since this level and further, we are entering the eventual consistency world, but that's life, nothing is for free. Also, we introduced two more problems. First one is, by accident, we can increase the load on our database, because if we launch hundreds of projectors, then those projectors need to query the database constantly to check for new events. That, of course, depends on the database and the queries, but still, it's possible. The second problem is more important, lags. So how often should I query my database to get new events? Each 3 seconds, each 1 second? I can imagine many systems when an additional second of eventual consistency is simply not acceptable. So what can we do about this before? Quick summary. Performance and scalability improved, and we introduced eventual consistency, increased database load with question mark and lags. Third level, another piece, which is event bus, and probably Greg Young would say that introducing this piece right now is not a very good idea. Well, if you have small load and 5 projectors, then yeah, introducing event bus will be an overkill, that's for sure. But this extra buffer between your event store and your event consumers, projectors, will give you very nice benefits. What are the benefits? Right now, we need only a single query to check for new events. So we definitely decrease the load on our event store database. And we can launch hundreds of projectors because message brokers were designed for such use cases. Unfortunately, the problem of lags still remains. So how often should we query the database? Maybe each millisecond. I suppose that launching 1,000 requests per second is not a very good idea. So we could start with something like this. Now we are saving events and in the same transaction sending them to the event bus. Of course, transaction on two heterogeneous systems is a very bad idea, so quick patch for that. The transaction right now is the same, and then after the successful saving, we can send the events to the event bus in a fire and forget style. This is the fastest possible way to fill event bus, but of course, you need to put some guarantees here. At least once delivery, so no events can be lost, and also events must be produced in exactly the same order. How to achieve this? Well, you can use, for example, sequence number. So each event should have its own monotonically increased sequence number. Let's say sequence number can be per aggregate. And before you send anything to the event bus, you need to check if the sequence number is +1, then yeah, I can send it. If it's -0 or -1, then this is a duplicate, I can skip it. If it's +2 or more, then I need to fill this gap from our event database. And in 99% of cases, you won't see any gaps, but you need to be ready for some restart, crashes, etc. And honestly, implementing this is not a piece of cake. We finally managed to do this right, and it's working since this day, but it's quite challenging. OK, let's validate our architecture right now. Query services are stateless services, so to scale this part, you just need to launch another instance, put some load balancer on top of it, and you're fine. Read model, yeah, we can scale this part also very easily. We can have a separate database per read model. Well, we can have a separate database per query, not a problem. We can launch hundreds of projectors because we will use good scalable event bus like Kafka. And yeah, this part will be also ready to scale. Scaling event store. This is tricky. I will get back to this part. And scaling command service side. This is even more tricky because command services must provide us consistency. And to achieve consistency, you have at least two options. First one is, of course, optimistic locking. But then you are forced to use a database that will support optimistic locking, most likely a SQL database. So your scaling capabilities here are limited by your database. On the other hand, you can handle concurrency on application level and implement something called single writer principle. And this way, you can use any database you want. So here you can use a distributed database. You can scale. But to scale this part in case of a single writer, you need a clustered, sharded solution with all its advantages and disadvantages. And I hope we will find some time to cover this topic as well. And here is our final version of Turbo Uber scaling architecture, where any of these pieces can be scaled independently and adjusted to your needs. Please do not start with something like that. My idea was to show you all possibilities, and your job is to find which level is the best for you. And let's say this is a Holy Grail. OK, summary of third level. Performance and scalability, very nice. And eventual consistency, yeah, for sure. Complex implementation and this idea of locking versus single writer, you can read about this more in this link. To cover this topic fully, I should mention about two other alternatives. So CDC, change capture data, very nice. It could be used instead of event bus. But this option is OK for a single host databases. For a distributed databases, I don't recommend to work with CDC. It will be a nightmare. Because we desire so much the streaming capabilities from our database, maybe we could use event bus as an event store. And here is a link to my CTO article about how to implement event sourcing based on Kafka. I hope that I'm not signing my contract termination right now, but be careful with that. I mean, Kafka for event sourcing will be a great idea for some use cases, but from my opinion, not as a general purpose solution. So make sure that you understand all Kafka concepts correctly and you know the limitation of such approach. Still, the article is great. Recommend to read it. Not covered today, but worth to check. Command sourcing, events, collaboration, really interesting topics. So let's say it's your homework. OK, so we know what we want to implement. Now, how to implement. And we have options like custom implementation, library, or framework. And if you look at event sourcing from domain perspective, this is quite a trivial pattern. We have only 3 main building blocks, so commands, event, state, and we need to implement just 2 methods on the state. So first one is process command and return list of events, and then apply event and return new version of the state. Between those commands, you need to persist the events. Yeah, so many people think that you can implement event sourcing by yourself. And this is partially true. Yeah, the domain part, you can implement this by yourself. But your application will be production ready when you also deliver a few more set but require features like snapshotting, failover, recover, debugging, sharding, serialization and schema evolution, concurrency access, etc. And implementing this from the scratch is a recipe for a failure. I mean, I completely understand you. I would also love to write my own event sourcing framework. But trust me, use something that is already implemented, tested by many programmers, many users, and do not reinvent the wheel. But using any framework has its hidden cost. Here's a classic JPA implementation where you have a business entity, maybe business aggregate, some domain code, and a JPA annotation. It looks OK, right? No. What's wrong with this code? We just mixed 2 very important responsibilities. First one is our domain code. The second one is some infrastructure instruction how to persist this entity. And someone could argue, so what? If I remove all these annotations, the code will be exactly the same. True, but this is a very simple example. And all tutorials are based on simple examples. Let's say that I would like to use a map of maps in my domain model. I suppose that translating such field to a JPA will be problematic. I'm not sure if it's even possible. Maybe it is, maybe not. Probably I will change it to something more JPA compatible. And personally, I hate such compromises where my persistence layer is dictating me how should I write my domain code. As Uncle Bob said many times, persistence should be only a plugin to my domain. Unfortunately, the same story applies to event sourcing frameworks. Here is an example from Axon framework. So user aggregate mixed with some framework annotations. The same story applies to Lagom framework. User entity extends persistent entity, and some imports to JSON format, whatever. On my domain level, I don't care about JSON. I don't care about persistent. I just want to write my business code. That's it. So how to approach this? Back to the basics. And you can start with proper packaging. Let's say in your domain package, put all the business-related event sourcing pieces, so events, commands, state, and application package is the place for your framework. You can check out the full source code example. The repository is pretty old, but the overall idea is still valid. This way, your event sourcing user could look like the snippet on the slide. So you have just 2 methods. I'm not saying that you should implement your domain in just 2 methods. Don't get me wrong. Those like entry points to your domain aggregate. No imports to any frameworks, just pure Scala. And this code will be trivial, or not. It will be exactly as complex as your domain. What's trivial here is how you will test this code. You don't have to launch Spring Context to test this code. You don't have to launch Actor System to test this code. You just need to write simple unit tests, and this is beautiful. OK, once again, application for all the set stuff, domain package for domain logic, domain validation, and 0 event sourcing framework imports. So if at some point I will decide that, okay, this event sourcing framework library is not good for me, then I will simply remove this application package and that's it. My domain will be untouched. This will, of course, never happen, but at least you are ready for it, and it's very good to have a separation of concerns in your code base. It's much nicer to maintain such a repository. Okay, library versus framework, because I'm using those notions very often. What's the difference? Usually, removing a library from your application is much easier than removing a framework. And a good example could be Akka Persistence versus Lagom. Lagom is a full-blown event sourcing framework, where everything is well organized. You just need to put commands here, events there, and Lagom will do the magic for you, unless you have a very specific business use case, and then you need to adjust this use case to the framework. Akka Persistence, on the other hand, is one level of abstraction lower. It will provide you all the necessary technical requirements to write good event sourcing solution, but you will need to handle more stuff by yourself. Also, you will get more freedom. Which choice is better? It depends. But I suppose this is a story for a whole new presentation. And I'm not saying that you should never use a framework. You should only validate all existing options and do it slowly, create some proof of concepts, and make sure that you pick the solution that is the best for you. When it comes to Akka stack, I could honestly recommend to use Akka Persistence typed. Still not a framework, but this time everything is well organized. It's much harder to do something stupid than in case of Akka Persistent without a typed API version, and I can honestly recommend it. Okay, so we know what we want to implement. How? Next question is where to store events. And options are like file, relation database, event store. Talk with Oskar Dudic about this option, MongoDB, Kafka, Cassandra. And this time, the storage selection depends on the previous choice. If you go with custom implementation, then yeah, you can use whatever storage you want. If you choose, let's say, Akka stack, then you are limited to relation database and Cassandra. That's not true. You can use other databases like Google Spanner, DynamoDB, and some others. But for sake of this presentation, let's say that you have a choice between SQL database and a distributed database. Okay, and relation database seems like a safe option for a start, because it is. Everyone is more or less familiar with it, know how to set it up, maintain on production, so it's a safe choice, right? That depends on your load. SQL databases and relation databases were designed to work well on a single host machines, and vertically scaling single host could be a problem sooner than later. That's why I recommend to use, or at least to analyze, distributed databases like Cassandra. Why? Because you will get partitioning by design. Your data will be spread across all nodes in the cluster. You will get replication by design. So in case of some node failure, you can always load the events from a different node. Leaderless architecture, so no single point of failure in comparison to Mongo, where you have classic leader-follower architecture, and in case of leader failure, bad things could happen. And Cassandra is optimized for writes. This is especially useful for event sourcing. So just 2 nodes can handle 100,000 transactions per second. Of course, this is copy-paste marketing. But if that's not enough for you, then you can simply add more nodes and scale it horizontally, almost in a linear fashion. Be aware that there is a growing alternative to Cassandra, which is Scylla. Scylla is basically Cassandra without JVM. The same concepts, the same protocol, just the implementation is in C++ and C*lib. Even bigger throughput and performance. But at this point, actually, I'm not sure about this point, but some time ago, it was not fully supported by Akka Persistence plugin. And here's an article about this. OK, so we know where to store events now, how to store them. And we have options like plain text serialization, so JSON, XML, YAML, and binary formats. And I know that most of you will choose JSON anyway, but let me show you some alternatives. First, let's compare plain text serialization versus binary serialization. Plain text serialization Of course, it's human readable. It's very nice and very convenient to just select some data, some events from database and analyze the results directly from the query. In case of binary serialization, you need an additional step. You need to translate the bytes to something readable. Is it a real problem? If you need to analyze something on production, you very quickly create a tool that will do this automatically for you. Yeah, such tool should be created up front, but there is nothing like a good motivation, and burning production is the best motivator you can imagine. With JSON, you can face very strange problems with number precisions. Just follow the links. And yeah, binary formats, by definitions, are more compressed than plain text serialization. The actual benefits depends on your events model. In my case, it was from 60 to 70% of saving on the disk space. And someone could say, yeah, but storage is cheap. Well, OK, storage prices usually go down. But at the same time, the amount of data we are gathering is growing even faster. Not to mention about replication required by some databases. And honestly, good, large, and fast SSD drives are not so cheap, in my opinion. All benchmarks are pretty consistent. Binary serialization is much faster than plain text serialization. This shouldn't be a surprise, since plain text serialization requires some additional steps. And last point, very important, schema evolution support. With good schema evolution support, you can version your event without typical versioning pain. So no more underscore v1, underscore v2. With schema evolution support, you can do this much nicer, much easier. And yeah, so clearly, binary formats are pretty nice. Now, which one should you choose? Java serialization is out. It's slow. It's dangerous. Don't use it. Cryo, very nice, very fast, but it will work only on JVM. So let's not limit our architecture only to JVM applications. Thrift from Facebook, when it comes to functionalities, it's almost the same as protocol buffers from Google. But I know protocol buffers better, so I picked this one for the comparison. So we have Avro versus Proto. And now I could spend another 50 minutes or so just explaining the difference between two of them. So we will do this very quickly and jump directly to the conclusions. Both will support many languages, although the devil is in the details. The support might be different. I mean, the level of support. Let's say in Avro, with Python, you are forced to use the generic Avro approach, so you will not use the full potential of Avro. On the other hand, Google protocol buffers support in Scala is way better than in Java, which is mind-blowing because it's usually the other way. Both are really fast. Both will produce very small payload size. Both will provide full compatibility support. So backward compatibility is obvious. You need to be able to read old events from the database. But forward compatibility is also important if you want to go with rolling updates and if you want to have independent projector updates. For example, I would like to introduce new event, but I don't want to update all projectors at the same time. With forward compatibility, I could do this later. So in both cases, you can add a field, remove a field, even rename a field. From my perspective, with protocol buffers, this is much easier. So what's the difference? And the difference is in schema management and overall impact in your domain. Yeah. So with Avro, you will generate the schema based on your existing code in most cases. So definitely you will write less boilerplate code. The cause of this is that sometimes Avro might knock to your domain and you will need to change something. Not always, but it's possible. Also, reader and writer schema distribution in Avro, in my opinion, is a pain. But let's not discuss this right now. When it comes to protocol buffers, the schema is first. Based on the schema, you will generate some classes, and it's much easier to keep your domain clean, but it will require to write a lot of boilerplate code, so methods like from something serializable to domain, from domain to something serializable. Which choice is better? It depends. If you want to read more, here's the link to my article about this, and you will get all the information about the slides I just skipped. OK, the last big question is what to put to the event payload. And most people will start with delta information. So delta event, for example, we want to emit an user funds withdrawn event, and we put only a delta amount of the withdrawal. And this is fine, this will work, but it will be quite painful to process such events from a projector perspective. That's why, let's say that we would like to create a projection that will send an email to a user if we spot that the current balance is below some threshold. It will be nice to have this information in the event payload and enrich the event with this kind of data. This way, the projector implementation will be extremely easy. You don't have to calculate anything. You don't have to access external resources. Very easy to write. The extreme version of events enrichment is to put the whole aggregate in the event. I've done this once, and I think in that case, it wasn't such a bad idea. Although, yeah, the cost is, of course, the payload size and the event schema you need to manage in future. Besides business information, most likely you will add some technical metadata like event sequence number, creation timestamp, event ID, useful for the duplication, command ID that was the source of the event, and correlation ID if you want to track the whole business process. OK, now we know everything. Or at least we know the directions. So let's introduce some event sourcing to our ecosystem. Where? Everywhere. No. This is the first major problem with event sourcing adaptation. As you, I hope, already noticed that this concept is quite powerful, but at the same time quite costly. So it's not worth to introduce it everywhere. In your core domain, you should choose even some subset of this core domain. And maybe this is a part for event sourcing, maybe not. So remember about this slide, and now we could move to more generic problems. And the first one you might think of is the replay time required to get the current version of the state. This is surprisingly fast operation to load 100 events and recreate the state, but many people ask about this, so let's start this one. Let's say that you have a huge aggregate with thousands of events, and in this case, you need to make sure that your event sourcing library or framework supports snapshotting. Snapshotting is basically saving your snapshot state every X of events. And then if you need to load the state, you need to load the latest snapshot and events after the snapshot. Another approach would be to keep everything in memory. Once you load the state, it will wait to handle next command. And this is awesome. That's why event sourcing based on actor model is so fast, because everything is memory. So it's really hard to write it faster once you don't have to query the database all the time. If you want to read more about that, go to the article from the slide. It's one of my favorite articles. OK, because everything is in memory, you can create out-of-memory exceptions. But out-of-memory exceptions in Java is not something new. Just make sure that you are not doing anything strange with your state, and you should be fine. Or learn how to use some memory analyzer tool. Next question, which is quite often, is, should my state be immutable or not? Well, by default, of course, immutable. This way, it will be much harder to create some out-of-memory exceptions. But as always, it depends. And in our case, when we were using immutable list, we were able to deliver 17 operations per second. When we switched to good old-fashioned Java 3 map, 2,200 operations per second. And this difference is so huge that it cannot be simply ignored. That's why we go with mutable state. Still, I'm pretty comfortable with that choice because actor is protecting the state. So you can go with mutable state in a reactive system, and it will work just fine. Before you switch from immutable to mutable, make sure that you really need it. Create some benchmarks. You might be surprised with the actual results. Fixing the state. OK, this one is boring, and this one is also boring. Handling duplicates. Oh my God. This is a nightmare in a distributed system. Let me tell you a story. This is a fairyland, and this first unicorn is called exactly once delivery, and the second one is called transaction between two aggregates. None of them exists. And you know, I'm a happy father of twin sisters. So when I'm saying that there is no such thing as exactly once delivery, trust me, I know what I'm talking about. So if someone is telling to you, you can achieve exactly once delivery in a distributed system, either this person is lying to you, or not telling the whole truth, or talking about something different, like effectively once delivery, because exactly once not exist. OK, so why duplicates? First, we can create some duplicates on producer side. Even if you are able to filter out duplicates here, which is possible, still we need to be ready for duplicates on a project or consumer side because of some crashes, restarts, etc. And the best way to handle this situation is to have idempotent updates. So processing the same event twice will not change anything. The outcome will be exactly the same. And this is the best solution. Unfortunately, some projections by definition are not idempotent. If you aggregate something like counting average or whatever, processing the same event twice will corrupt the projection. And in this case, you should try to achieve something called effectively once delivery by the duplication. How to do this? Well, in the same transaction, you need to save your update and sequence number, let's say, and before you change anything, for the next time, you need to check if the sequence number of the event you are processing right now is +1. Then, yeah, you can process it. If it's -0 or -1, then this is a duplicate. You need to skip it. If it's +2 or more, then it means that you have a gap in your event bus. And the only way to fix this is to, you need to fix the producer of the events, not the consumer. Surprisingly, not all read model storages support such transaction. For example, in Redis, transaction is something completely different. So make sure that your read model database will support such option. If you don't have a sequence number, you can use event ID for the duplication, but then you need to store a history, some history of event IDs. And this brings us to the next problem, which is a broken read model, where when you can break your read model, two main reasons for that. So software reason, a bug in the code, and hardware reasons. So some read models are more fragile than others. And Redis is a very good example, once again. You can always lose some data in Redis, actually quite a lot of them, depending on the configuration. So in this case, thanks to event sourcing, you can always delete the whole read model and rebuild it from the scratch and read all the events. And this is really awesome. This is great. I use it so many times on production for many different problems that it's hard to count. But in some cases, processing billions of events might take some time. And especially in case of hardware failures, you want to fix the problem as soon as possible. And in this case, you could use something called manual offset management. It's technology dependent. It's possible in Kafka, where in one transaction, you can save your read model, update, and current offset from the message bus. And in case of hardware failure, you can always get the latest successfully saved offset and start processing events from this offset. So that's the recipe. OK, multi-aggregate transactional update, second unicorn. If you need to update two aggregates in transaction, just look at this as a transaction between two different microservices. It's a red light and time for a pause. Maybe you should start with rethinking your aggregates boundaries. Maybe you have two thin aggregates, and if you join them, you will very quickly eliminate this problem. Sometimes your aggregates boundaries are fine, and you still need to handle this situation. And the only way to handle this right is to apply compensating action. And compensating actions could be optimistic and pessimistic. Those are not official names. I just made it up to explain you how you can approach this problem. So let's say from pessimistic compensation perspective, we are creating very simple application that will allow user to buy some tickets to some cinema shows. And we have two aggregates, user aggregate with some funds that could be charged, and the cinema show where you can book a seat and the seat number is limited. So the business flow could be as follows. First, we need to charge the user. Then we need to book the seat, and that was the last seat, so we are entering the sold-out state. Great. But our application usually are used by many users concurrently. So right after charging the first user, another user could book the last seat, and now this booking will fail. It will be nice to have a transaction here. But no, you should avoid such things. So the only way to fix this situation is to apply compensating action. And in this case, you simply need to refund the money. And this is a pessimistic version from user perspective because user is first charged. From the optimistic perspective, this way you are now first booking the seat and then charging the user. So in case of concurrent booking, we can enter an overbooked state. And now, should we charge the user? Probably in cinema business, it will not be a good idea. But in case of buying tickets for some planes, well, overbooking is okay, and it's a part of a business strategy. So that's not a problem. And actually, I noticed this many times that in case of very popular shows, especially in theaters, they can always add an additional chair, and overbooking is not a problem anymore. So different business strategies, different solutions. One thing is missing in the story, how to implement this. And for that, you will most likely end up with Saga pattern. And Saga pattern could be based on choreography, where you just consuming 2 or more event stream from different aggregates and checking for some inconsistencies. Or Saga could be based on orchestration, where you have one place with the business process step by step. And honestly, the first option is way easier to implement, but the second option is much easier to understand. Unfortunately, Saga pattern is quite painful to implement. It must be persistible, so in case of some restarts, crashes, you should also restart the Saga process. You cannot assume any order of the events because you are consuming completely separate event streams, so order should be irrelevant. You will be always limited to some time window. Let's say that we just noticed a charged event, and now we are waiting for 10 minutes for booked event. And after 10 minutes, okay, probably we have some inconsistency. We need to apply compensating action. I said probably because the booked event can arrive to us after 12 minutes. And that's why compensating action must be commutative. So to implement all this stuff, it will take some time. A few more links for you and a piece of advice from my side. Try to avoid sagas if you can. In some cases, you can do this by creating larger aggregates. For some frameworks, it's not a problem. Yeah. Event sourcing and Rodo. This one should be quick. Okay, so your application should give users something called right to forget. And how to do this with event sourcing where you cannot simply delete events? Well, the technique is called data shredding, so all sensitive information should be encoded. And then if you need to remove data of some user, you just need to remove the encoding key. Sounds easy, but not so easy to implement. The encoding key management is quite painful. Also, you need to remember about retention policy of your message brokers, backups and logs, and also migration the data before Rodo. So my advice here is to not use event sourcing for Rodo stuff. Most likely you don't need it. I mean, to have event sourcing for this case, relation database will be just fine. Okay, last or almost last point. In our final version of architecture, I mentioned that we will use a sharded cluster solution. And with cluster, you can face a very nasty problem, which is a split brain. What is split brain? Let's say that we have a cluster with 5 nodes and some load balancer on top of it. Load balancer is a dummy machine. It will just route all the requests in round-robin fashion to all nodes. So the first request to update user with ID 1 could be routed to node 5. But node 5 is in the cluster, and this node is aware that the node responsible for this user is actually the node 1. So it will redirect this request to node 1. Node 1 will handle it, and yeah, cool. Now we have a disaster in our DC, a broken switch or something like that. And in this case, node 1 and node 2 are working just fine, but cannot communicate with 3, 4, and 5. From the load balancer perspective, nothing changed. All nodes are working fine, but they just created 2 separate clusters. So in this case, the command to update user 1 from node 5 will go to node 4, because in the smaller cluster, node 4 is responsible for user 1. Next request could go directly to node 1, and in this smaller cluster, node 1 is responsible for user 1, and there you go. Classic split brain. Fixing the state after such failure is the biggest pain you can imagine. So what can you do about this? First, be aware of this problem. Second, for example, in case of Akka cluster, there is a dedicated solution for that, which is called split brain resolver. Make sure that you enable it and configure it correctly. A few more advices when it comes to clusters. Remember about the split brain. I will repeat myself. You should enable very good monitoring and alerting, and you need to have data about your cluster to monitor it very, very detailed. You should run a lot of failover tests, try to break your cluster, however you can create your own chaos monkey. Cluster should be also deployed on dev and staging environment, not only on production, just to test it better and to notice some problems faster. And keep it as small as possible when it comes to code base, so remove unused functionalities, and when it comes to number of nodes, cluster with 5 nodes is way easier to manage than cluster with 15 nodes. Okay, summary of this whole presentation. Event sourcing is awesome, it's great, you will love it. The second time you use it. The first time it will be painful. To be less painful, carefully choose your event sourcing library and framework. Take some time. Do it slowly. There is no perfect database for event sourcing. Only good compromise. Take some time and understand schema evolution of your events, state, event commands. And I'm not talking about hours here. I'm talking about days or weeks. Really, this is really important. Eventual consistency is your friend. Do not fight with it. Learn how to deal with it. Scaling is complex. No magic here. If you launch Kafka cluster, Cassandra cluster, Akka cluster, it will require a lot of work. But at the same time, once you do it, the reward will be proportional to the effort. And the whole event sourcing is like turning your database inside out. Finally, asynchronous, decoupled, event-driven communication makes sense in this case. And last point is a little bit philosophical. Once you wrote your application where the main focus is on processing stream of events, you will realize that all big players using the same techniques. So Netflix, Facebook, Twitter, whatever. All of them using the same patterns in their systems. Well, most of the DB engines use the same patterns. So write something to the log, process it later. That's why I really recommend to try it, to expand your toolbox with this pattern, with this architecture style. Because this is the recipe for building reactive, elastic, performant, event-driven applications, distributed applications. And last point, if you want to go deeper, but you don't have some time to do this by yourself, some time ago we launched a few online on-site workshops about how to start with factor model, how to create reactive event sourcing solutions, then how to scale them, then how to measure the performance of such solutions. Thank you very much. If you have any questions whatsoever, just ask me now or later. And if you could rate me. Thanks.